So we want to do social choice with boundedly rational agents. So that's the ultimate goal. Okay, so when you have fully rational agents, we know how to do welfare analysis because essentially, people's choices reveal their preferences, and then we just use their preferences to evaluate public policies, right? Now, if people are not fully rational, then their choices no longer reveal a coherent or consistent preference, and we are not sure how to, how to evaluate social policies. So what should we do? Okay, so if we want to do welfare analysis when agents are not fully rational, how should we go about that? All right, so the problem is already there with just one agent. Okay, so there are clearly two problems. There is an aggregation problem in the end, but you already have the problem with just one agent. How do you evaluate the welfare of a single agent if this guy is not fully rational? Okay, so that's the first step, and it seems to us that we should get an idea of how to solve that problem if we want to do social choice with boundedly rational agents. So this is what we do here. All right, so this is I wouldn't say it's based on Bernheim-Rengel, but so this is the work that exists, that's in this spirit. So everything will be extremely abstract, but very simple too. So we have a finite set of conceivable alternatives that's unstructured. And then we will be looking at the set of all subsets of this set, subset of size 2, say. And then we'll look at choice functions. Okay, so we want to model behavior that is not necessarily rational, and we don't want to make any restrictions at all on behavior. Okay, so we are going to look at actually the class of all possible choice functions. So a choice function is simply a mapping that selects from any possible feasible set a single alternative. So this is the simplest case. We are not looking at correspondence, we are just looking at functions. Okay, so here is what has been proposed by Bernheim and Rengel. So that's sort of a weak criterion. So what they notice is that even boundedly rational agents somehow display a minimum form of coherence that tells you something about how to evaluate welfare. Okay, and so what they suggest is that based on a choice function C, you should say that alternative X is better than Y if it is the case that Y is never chosen whenever X is there. Okay? All right, so that seems like a fairly uncontroversial idea. Of course, so what they show essentially is that this relation is acyclic, and that's really not very difficult to show. But the problem with that, of course, is that typically this relation is going to be very incomplete. Okay? And we want to do more. All right? So that's so what we want to do is to derive a complete ordering. Now, this obviously is asking a lot from very little. So what can we do? Well, what we can do is, instead of doing what they do, just take one choice function and look at it. Look at all choice functions together, and then impose conditions on how the orderings assigned to various choice functions should be related. Okay, so that's what we are going to do. Okay, and so formally, the object that we are going to look at is this. Okay, so we are simply going to look at, so a solution to our problem is simply going to be a function that assigns an ordering to every choice function. Okay, so it's as simple as that. All right, is everybody with me? So that's the object that we are going to look at. Okay, so so just to make sure, the choice functions are choice functions; they are not correspondences, and this mapping is also a mapping; it's not a correspondence. So, and it is a mapping into the set of linear ordering. So that's also, of course, asking a lot. We are asking for a strict ordering based on the choice function. Okay, so that's really very demanding. So let me just mention a few things about here. One way that I like to look at this problem is as an extension of tournament theory. Okay, so this is in fact, if you were to look at choice functions that would be defined only over subsets of size 2, then you would try, in fact, to construct an ordering based on a tournament. And there is a huge literature on that, and there are plenty of interesting solutions, completely different ideas. There is a lot of stuff there. Okay, and here, of course, we have a much richer class of possible solutions because, of course, choice functions are much richer objects than tournaments because we have information about what is chosen not only on pairs but on all subsets of all sizes. Okay, so just to give you an idea, that's the size of the of the set of solutions when there are 4 alternatives. Okay? All right, but the point that is more important is to realize that there are way more choice functions than orderings. Okay, so again, with 4 alternatives, there are only 24 orderings, but there are 20,000 choice functions. Okay, so that means that we will have to pack together plenty of different choice functions into the same order, right? So that's just something that you are not going to be able to avoid. Okay. So yes, just to so I'm not going to talk too much about the literature, but we can discuss it. Okay. So this is an abstract and model-free approach. So abstract means simply that there is no structure on the set of alternatives. Model-free. So this refers to the debate in the bounded rationality, between people who do model-based papers and people who write model-free papers. So basically, we are not going to assume any theory of bounded rationality. So in fact, what this means is that we are looking at the full class of choice functions. Okay, and I think this is important in our context because we are doing normative analysis. Okay, it's okay if you do positive analysis to say, okay, I'm just interested in one type of boundedly irrational behavior, and I don't care about the rest because that's what I want to study, and I want to do this to describe that. But here, we are we have social choice in mind. It's it's the Arrovian approach. We don't want to restrict behavior in any type of way, right? Ultimately, we want to tell these people in advance, here's what we are going to do with what you report, and we don't want to forbid them to behave in any kind of silly way that they would like to. Okay, so we have this object f, and now here are the axioms that we suggest. Yes.
Just wanted the property Bernheim and Wrangel assume is actually restricting behavior. There are many boundary rational models that do not.
Absolutely. Yes. But it is also very incomplete. But indeed, yes. But so again, I do not want to enter into the debate, but it is very reasonable if, again, you don't have, in the model-free approach, if all you have is this observation, this set of observations.
I think model-free. So what he's saying is that there are some bounded rational model, their conjecture is wrong. Hence, there is some kind of model in their minds that you can use. So I think the model-free, that's a wrong terminology, because I can give you one model, their implication is completely wrong.
Yes.
Hence, it cannot be model-free by definition. Maybe it applies to a group of models. We don't know which one.
A group of models so the point is, it's the full class of choice functions. Okay. And I really don't want to enter into this debate. I mean, there are advantages to both approaches. This really reminds me of what empirical econometricians do. They fight. Those people who do structural and people who do reduced forms, and they just fight. But of course, you can, and that's a bit the same thing. We can learn things from both approaches. If you assume a model, then you can say more things. But of course, your model could be misspecified. And if you don't assume a model, then of course you don't run that risk, but you can say only fewer things. Okay, so, okay, anyway. All right, so here is the first axiom. So that's simply saying that if the choice function that we face is rational, then the ordering that we are going to assign to it is precisely the ordering that is behind that choice function. Okay, so that means we are simply non-paternalistic. Everybody who is actually behaving rationally will be assigned the ordering that he is maximizing. Okay? Second condition, it's a condition of neutrality. Again, we don't have any structure on the set of alternatives. So this is simply saying, it's the usual thing. If you permute a choice function, then the ordering that you are going to assign to this permuted choice function is simply the permutation of the ordering that you were assigning to the original choice function. Okay, so it's a neutrality condition. So I don't think I need to explain too much these axioms. And then we have a third one, and that's the novelty here. And so for the third one, I need to, introduce one definition. So this is an abstract model, so there isn't too much structure, but there is some structure. There is a natural idea of betweenness. Okay, so what I was talking about betweenness between ordering, there is also a natural idea of betweenness of choice functions. Okay, and it's there. So pick two choice functions. So it's here C and C prime. So when am I going to say that C double prime is in between them? Well, simply if in any set, what it chooses is something that is chosen by one of the two. Okay, so if these two agree, then I have to pick the common thing that they pick. And if they disagree, I cannot pick a third thing. Okay? All right, so in a descriptive sense, this behavior is kind of in between. Okay, it's sort of bounded by these two choice functions. All right, and now the idea is what? The idea is to say that this betweenness relation should somehow be reflected by the orderings that we are going to assign to these choice functions. And we are not going to go that far. We are going simply to require that if it happens that the ordering assigned to C and C prime is the same, then we also assign that ordering to anything that is in between C and C prime. Okay? All right, so that's it. All right, so let me describe a solution now. And I think Salvador described it, right? If you remember Salvador's talk, it was about starting from the bottom instead of the top. And he described this solution that does start from the top. And it's sort of a folk solution. I've seen it in a book by Arrow and Reno. It's one of the exercises in your book. Maybe you can tell me more references. I don't know. Okay. And then it's in a survey. That's actually an interesting survey by Buissou. Okay. So how does it work? So Salvador just mentioned it. So give me your choice function. I'm going to construct the ordering like this. I'm just going to put on top of the ordering what you choose from the full set. And then I'm going to put second what you choose from the set that remains after I have removed your top, and so on. Okay. Okay, so this solution is clearly admissible. So that was my first axiom. So if your choice function is rational, this is going to construct the ordering that is behind it. It's also neutral. I mean, there's, I don't need the names of the alternatives in order to define this. And it is also persistent, so that's the third axiom. So why is that? Well, because take two choice functions. And so remember, that's in the premise of the axiom. So suppose that they do give the same ordering. So what does that mean? That means that they choose the same thing from the top. Say from 1 to 3, they choose 1. Then you go to 2, 3. For them to generate the same ordering, they must both pick 2. Okay, and now anything in between will also pick 1 from 1 to 3 and 2 from 2, 3. Okay, and that's all I need to know in order to decide that I'm going to assign to it the ordering 1, 2, 3. Okay, so that's clearly the case. And here's the theorem. So that's all. I mean, these three axioms characterize this solution. Okay, how much time do I have?
Around 10 minutes.
All right. So I want to explain the proof because that's the only interesting part of the paper. So let me show you the proof for three objects. Okay. So x is equal to 1, 2, 3. So these are the three alternatives. And we start from a solution that satisfies our three axioms. So that's f, and s is the sequential solution. So I want to show that f is equal to s. And because f is neutral, it's enough to show that the set of choice functions to which you are going to assign the order 1, 2, 3 is the same for f as it is for s. Okay? So let us show that. So what is it actually for s? That might be a good thing to do here. So we are in the three alternative case, so there are 24 choice functions. Since this is a neutral solution, there will be 4 that will give rise to the ordering 1, 2, 3. And so what are they? Well, all those that pick 1 here and 2 here. Okay, and in between you can do anything you want. Okay, so you can do 1, 1, you can do 1, 3, you can do 2, 1, or you could do 2, 3. Okay, so this is, sorry, 2 here. So this is the set of choice functions to which the sequential solution assigns the ordering 1, 2, 3. Okay. All right, so now the important thing is to notice that you can view the set of all choice functions as a Cartesian product. Okay? It's a point in a space that has as many dimensions as there are feasible sets. Okay, so you can choose one alternative from 1, 2, 3, one from 1, 2, one from 1, 3, and one from 2, 3. And now the key thing, all right, so just to rewrite this, so notice that the inverse image of the ordering 1, 2, 3 under the sequential solution is in fact a Cartesian product, right? So you can choose 1 and only 1 from this set, you can choose 2 and only 2 from this set, and you can choose whatever you want there. Okay, now in fact, the persistence axiom tells you precisely that. It tells you that the inverse image of any ordering, in fact, must be a Cartesian product. That's what it says, because if you have two choice functions that give you the same ordering, then the box of choice functions that are in between these two will also give the same ordering. Okay? So we know that the inverse image has to have this form. So what is left to do is to show that this Cartesian product is equal to that one. Okay? Okay, so what do we know? Well, by admissibility, I know that the rational choice function, the rational choice function based on the ordering 1, 2, 3 should be in the set. So that means that this set should contain 1, that one 2, and that one 2. And this one should contain 2. All right, so these are the first two things that I know. What else do I know? I also know that the ordering 1, 3, 2 cannot be assigned, the choice function based on the ordering 1, 3, 2 cannot be assigned the ordering 1, 2, 3. So that means that I have to rule out 3 from that set. Because since 1 is in each of them, if 3 were in there, then the choice function based on the ordering 1, 3, 2 would be assigned the ordering 1, 2, 3. Okay? So that means that this set is in fact 2. Okay, so that now I know. All right. So what is there that remains to be shown? So well, we are halfway there. Okay, so now we exploit neutrality. Well, what more do we know? Okay, so we know that there are exactly 24 choice functions, and so by neutrality, our class, so basically the product of these 4 sets should have size 4. Okay? So that means, since we know that gamma of 2, 3 has size 1, the product of these 3 should have size 4. All right, so that already tells you that the first one cannot have size 3. So let me show you now, so it must have size 1 or 2. Let me show you that it cannot have size 2. Okay, so what would happen if it has size 2? Okay, so let me draw a picture. Well, if it has size 2, there are 2 possibilities. Okay, so 1, 2, 3, 1, 2, 1, 3, 2, 3. Okay, so I'm assuming that this set gamma has size 2 here. I already know that here it's just consists of one singleton, which is 2. I know that the product should be of size 4. So either this is of size 1 and this is of size 2, or this is of size 2 and this is of size 1. I know also that 1 should be in there. So 1 is here. 1 is here, 3 is there. 1 is here. There, I don't know. Let's put A. Okay, here we have 1, here we have 2, and here we have 3. All right, now look at this. So that means what? That means that there are 4 choice functions, which are 1, 1, 1, 2, 1, 1, 3, 2, A, 1, 1, 2, and A, 1, 3, 2. So in that class, we have 2 choice functions that are cyclic. But how many cyclical choice functions do we have in total? 6. So in each class, there should be exactly 1. We have 2, so that doesn't work. And if we do this, what do we get? We get 1, 1, 3, 2, A, 2, 3, 2. Sorry. Yeah, it's 1 here. Thank you. Thank you. So 1, 1, 1, 2. One, 2, 1, 2, A1, 1, 2, and A2, 1, 2. So how many cyclical choice functions do we have? Well, 0, right? So here we have 2, here we have 0, but we should get 1. Okay, so that cannot be, right? So this set cannot be of size 2, so it must be of size 1. And if it is of size 1, so we know that this is of size 1, so we know that this is 1. We know that this is of size 1 too. We know that the total must be of size 4, so this must be 1, 2. Okay, so that's the proof. All right, and I guess I'm basically done. I wanted to, okay, I'll stop there.
If we relax persistence a little bit, instead of taking any C function, C and C prime, I would like to take one of them to be rational guy.
Yes. Right. So this is indeed something that we've been looking at. Just to, well, I mean, the thing that we've been looking is this. Okay. So you take a choice function and then you take the rational choice function generated by the ordering that you assign to that choice function, okay? And now if you somehow move from the choice function that you started from to the rational one that you assign to it, well, the solution shouldn't change, right? It should remain the same, okay? So that's a natural weakening. So characterizing the whole class of solutions that satisfy anonymity neutrality and weak persistence is something not obvious at all. So what is true is that this is not enough. Okay, so we do have examples that satisfy this and the other two axioms, and that are not the solution that I just described. Basically, you could think of the persistence axiom as some form of convexity of the inverse images, and something like this is something like a star-shaped assumption, and that's much harder to work with. Thank you.